Okay, everybody, we're going to get started with today's webinar broadcast. Again, my name is TJ Willits with Veolia Water Technologies, and I want to welcome you to today's webinar entitled ZLD and Byproduct Recovery Using Advanced Evaporation Technologies. I have just some intro slides to get through here, some housekeeping slides. Obviously, you should be hearing me speak now. If you're having trouble with your audio anytime during the broadcast, there are two options for connecting to listen to today's presentation. You could listen through your headphones or your computer speakers, or if you're having any issues there, you could toggle that switch and go back to a phone call, and you can call in and dial in on a call-in number. And just to let everyone know that your microphone is automatically muted because we have so many people on the call here today. No worries though, even though you're muted, we want to make these sessions as interactive as possible. To interact with our panelists, we have a questions panel on the right side of your GoToWebinar screen. If you want to just put in the chat box your question there, we're going to be monitoring those questions throughout the broadcast. So anytime you feel like you need to ask a question, go ahead and enter it there. Then we're going to try to work in as many of those inquiries as possible at the end of the normal presentation time. And just to let everyone know that this webinar broadcast is part of our 3-week interactive webinar series here. We're on the last week of that 3-week series, but no worries. We've recorded all these webinars and they're all available online. We have a couple webinars left for this week. So if you want to register for those webinars that are upcoming, you can do so by going to our website, veoliawatertech.com. And as I mentioned, we recorded all the webinars we've done so far. We've even went as far to record all the webinars in the past and make those available online. So we have 30 or 40 webinars available right on our website that you can watch on demand. Again, our website is veoliawatertech.com. To provide you with a participation certificate, what we're going to do is that the system GoToWebinar will automatically email you that PDF certificate tomorrow after the webinar. So be on the look at that, and it'll be about 24 hours after the webinar closes. You'll get that in your follow-up email, and you can download that and show credit that you've participated in today's live broadcast. And then your feedback truly does matter. We're trying to always improve these webinar broadcasts. Something that we're going to do that's a little bit fun. Anyone who takes the survey right after the webinar, you'll be presented with a short survey. It takes just less than a minute to complete, but we're going to put everyone in a drawing for a Amazon gift card, a $25 Amazon gift card. So if you want a chance to win that, as well as giving us some feedback, go ahead and just take that quick survey. Okay, and just the last slide, talk a little bit about Veolia Water Technologies. In case you are not familiar with us, our company is set around 3 key areas related to water and wastewater treatment. That's developing amazing technologies that help customers figure out and treat their water and wastewater needs. We have the ability to bundle those into developing a comprehensive project using engineering procurement. And then lastly, we have a comprehensive set of services that we support our customers, whether it's before, during, or after a project as well. And now we're going to transition to today's technical presentation. We are fortunate to have 2 panelists with us here today to present. Our first panelist that you're going to be hearing from, his name is Bradley Young. He is a PhD in environmental engineering and is also a professional engineer. He's been working with Veolia for nearly 10 years in R&D and product development. Also with us all the way from our VWT Italy branch is Michele Gallucci. Michele is a chemical engineer in sustainable processes with experience in pharma and wastewater industries. So at this time, I'd like to turn it over to our first panelist, Bradley. Bradley, are you with us?
Yeah, I'm good. Can you hear me?
Yes, Bradley.
All right, thank you. All right, so thank you and good morning to everybody joining. So we'll first kind of just review the agenda. So we'll start the presentation with why evaporation. Evaporation is no secret. We've all at some point in our life boiled water. You've transformed a liquid into a vapor phase. So we'll look at why you would want to do that with your water or wastewater treatment needs. We'll look at evaporation under a vacuum. So this is what EVALID and VWT is using to reduce energy. We'll look at the types of evaporators that we offer, each different product or model. We'll look briefly at how we're optimizing heat transfer and how that can provide some energy savings. And then McKelly will go over some case studies which cover a very wide range of industries, both in North America and throughout the world. So to give you a good view of where these technologies have been applied and how they did provide benefits. And lastly, we'll wrap it up and take some questions. So the first topic is why evaporation. As I said, evaporation is, we've all done it. Basically, if you have a water source and you can then evaporate it, you'll create a distilled water. So that will be when you condensate your vapor, and you'll be left with a product. So this can be done on a very wide range of applications and a very wide range of market segments. You can very quickly look and see it covers a very huge list. So we're looking at wastewater treatment. We're looking at industries where you need to reduce your disposal volume. So if you have something that's very expensive to discharge, we're looking to make that volume reduced. Zero liquid discharge, which is one of the topics of the presentation. Places where you want to reuse water. So if there's a corporate sustainability goal, or if water is a valuable resource in your facility that a reuse portion could be valuable, we want to look at that. And also byproducts recovery. So some wastewater streams, even though it's a source of pollution, if it's sent to the municipal sewer network or being disposed of, that may contain a valuable byproduct. And if we evaporate the liquid out, we can retain that valuable byproduct and then send it to market. So that could either be sold to other users, or it could be given for free, for example, for agricultural use. It could be farm feed, and then you're therefore not paying to get rid of your waste, but rather someone is taking it and you're part of the circular economy. So this can cover a very wide range of markets. As I mentioned, you're looking at healthcare, pharmaceuticals, the chemical industry, surface treatments, biogas and biofuels, food and beverage. There's a lot of different applications in food and beverage where this is applied. McKelly will touch on a couple of those. We're looking at waste, microelectronics, another popular one, oil and gas, power, mining, automotives. So really it covers, you might laugh, but it looks like it basically covers the entire segment. But like anything, there's going to be niche places. So you aren't going to want to always use an evaporator for every wastewater treatment need, but there are definitely places where this is going to be your best technology option. So that's what we're here to provide some education on today. So the key drivers for considering evaporation, the first two kind of go together. So you have high disposal costs. So this would be, say you have to truck your wastewater out of your facility. Having a high volume is going to certainly increase those disposal costs, as will if you have local legislation. So some places may be connected to a municipal sewer network. Each municipality then has the right to levy surcharges based on the water quality that's being sent. These can vary from very high to very low, depending on where facilities are located. But the point here is if you have a high disposal cost, you could have a very concentrated wastewater stream. It may be difficult for a biological system or a traditional physical chemical system to deal with. But just because you have a smaller volume doesn't mean you're going to pay a lower fee, because you do have those high concentrations. Or if you have a medium volume that you're just looking to reduce. So that's one area where evaporation is going to be a good technology to look at. As we mentioned, the request for separating reusable or valuable components. So this could be corporate sustainability, it could be economical. So if you have, again, one of these high concentrated wastes, smaller volumes, if we can pull out those components which are traditionally considered a pollution and push those into something that's more valuable, for example, as I used before with farm feed, this is going to create both a positive economic value for the industry, but also for the environment and what we consider circular economy. You could optimize the OPEX, so this could be basically energy or chemicals consumptions for existing plant. Water impact, we want to reduce the amount of water used for your product. So in a way, this could be reuse. So our distilled water, as you'll see from McKelly's case studies, is going to be of high quality, and that can then be reused on site depending on your processes. Difficult wastewaters containing salts, oils, detergents. So if you want to separate those. Another popular one is concentrate from UF or RO. It's no secret that if you have membrane facility on site, it produces a very high quality of water. This is often used for reuse. So if you have one of these UF or ROs, you're not actually going to be treating the water. You're simply pulling the water through your membranes, and then you're concentrating your problem into a smaller volume, but it's still going to be potentially difficult to manage. So now you have this reused water and you have this difficult to manage concentrated source. So where evaporation can come in handy is that we'll take that difficult portion that is now more concentrated and we'll squeeze it even further, which you'll see in the next few slides. So basically, we're going to take that smaller volume, which is more problematic, and reduce that volume by using our evaporation technology. The other one is if you have basically a difficult to degrade. So if you have a lot of COD, traditional biological system won't manage these difficult to degrade or non-biodegradable components, then evaporation is a good way to get rid of the COD. And that kind of loops back into our top bullet points where you can be paying surcharges and have a pollution problem to your municipal networks. So the new technology, the one that we're looking at with eValid, is vacuum evaporation. So start with a kind of a neat slide. I like it. The first thing you notice is probably the beautiful pasta. So as I mentioned, we've all boiled water. We've cooked pasta. Due to current events, I'm cooking a lot of macaroni and cheese for my son. But basically, everybody knows, depending on where you're located, it's going to be somewhere around 212 degrees Fahrenheit or 100 degrees Celsius to evaporate your water. We put it on a stove, either gas furnace, a gas oven, or electric. And at some point, you're going to end up boiling. So this takes quite a lot of energy. The point that people don't often think of is that 212 degrees Fahrenheit is at sea level. So if we create a vacuum, we go to a negative pressure, we can actually reduce the boiling temperature of water. So we're using some physics to our advantage. By doing this, we're lowering the boiling temperature, so you're going to have corrosion reduction, which extends the life of your mechanical components in your system, in the product. We're using a vacuum, so we're pulling the oxygen out. This reduces the interaction on the surface with the oxygen. You reduce your pitting, which again reduces corrosion, and you end up extending the life of the components inside of the product. It's a closed loop, so it's completely, you have covers, it's completely closed, so there's no emissions to the atmosphere, which is a nice benefit, especially in the environment we're in today. And the biggest driver here is that we have less energy needed. So by boiling water at a lower temperature, you'll see in the different models how efficient this is, that we're going to require less energy, and that then therefore reduces the operational cost with evaporation. So people would normally think that to evaporate water, you need to put a lot of energy in. It's a very costly technology to operate, but because we're extending the life of our components inside, we have lower O&M. We're also reducing the amount of energy that needs to go into the technology to boil. So therefore, we're reducing your electricity consumptions or your heat generation consumption as well. So what are we trying to do? When we say squeeze your water, basically we have a wastewater source, which comes into our evaporator at 100% strength. So this is your full stream that we're trying to treat. We add energy. We are then going to take the vapor and we distill it. So we condensate it, it becomes a liquid again. That distilled water is going to encompass somewhere between 90 and 95% of your initial wastewater stream. So that's a clean water, it's a distilled water. McKelly will show you more or less the different qualities of distilled water depending on application. And what's important is that then you're only left with about 5% to 10% of your initial wastewater volume as concentrate. So this gives you a very high separation level. You've got a water that potentially could be used for reuse in your distilled water, And then if you think of it as a concentration thing, if you were having to discharge 100% of that water, you've now concentrated what you have to get rid of down 10 to 20 times of the initial waste volume. So if you're trucking water, if you're trucking waste, then this is significantly reducing the volume and significantly reducing your costs you have to get rid of. And if you want to go to zero liquid discharge, basically the point here is that we do a second stage evaporator. So you take that concentrate from the first evaporator, and then you run it through a second stage, and you're going to end up with a really dry component. So after your second stage evaporator, we can get sludge concentrations up to 90% of dry matter. You can see in the pictures here, it's really, really dry. And this basically makes it so you're only hauling solid material, so your disposal volumes are going to be extremely small. Your disposal costs then are going to be extremely small, and you've got a lot of distilled water which you're able to use for different beneficial reuse areas. This also then gives you your valuable matter for recovery. So as we said, it could be sugars from candy production, whey protein. Kelly will talk about a case study with whey protein where he'll explain further, but basically it stabilized the whey and then they were able to reuse for future use. So how and where is eValid applied? Pretty self-explanatory, but basically if you have a complex treatment unit or a wastewater treatment plant on site, we can apply an eValid evaporator as a unit of operation. So let's say you have a difficult stream in your wastewater plant, it's causing some problems, some upsets for your biological or your physical chemical system. We could then put an evaporator on that treatment line. So then you can remove that problematic stream from your wastewater treatment. We'll basically concentrate the waste, will produce the distilled water, and that will free up your biological or your physical chemical system. Or it can be a standalone treatment unit. As standalone, basically you have a wastewater source, we can bring the eValid on site, and this is basically on its own going to reduce your disposal costs and recover potentially beneficial byproducts. So there's no one size fits all. Basically, if you have a need, it can either go inside of a system or it can be in its own wastewater treatment plant. So what types of evaporator technologies do we have? There's three families of technologies. There's the PC, which is heat pump, the AC, which is hot cold water, and the RV, which is mechanical vapor recompression. All of these families are standard products. So they're skid mounted. They all come with the automation pre-done. They're all linked to our Aquavista platform, so you can subscribe to service for remote support, service and maintenance. So it's easy to implement on site. The other key point is that each one has individual aspects to it that make it either a more or less better fit for each individual industry or each individual location on your facility. Today, we're not going to go into very detailed explanation of each model. We'll give more of a bigger overview. And if you have questions on more of the physics or each individual little component of a system, we invite you to ask the questions and we can get back to you after the webinar for the more extreme detailed answers. But as I mentioned, we can certainly give the overview. So the first one is the heat pump evaporator. You'll notice it's for smaller flows. So this goes up to 5 GPM. This evaporator works under a pretty significant vacuum. So you can see that we're evaporating water at 100 degrees Fahrenheit, which is approximately somewhere around 40 degrees Celsius. So right away, you can see the energy savings in before, if you just have your pot on a stove to boil your macaroni, we're looking at 212 degrees. Now we're down to 100. So you have a very significant energy savings there. Everything's self-enclosed. So the way you can think of the heat pump to work is there's a freon gas inside. So it works somewhat like, I guess, a heat pump at your house or your air conditioner. And as that's circulating, we're going to go through heat exchangers. The important point here is to know that there's two series. So the F series is forced circulation. Basically what this means is that your concentrate, we're going to push it through tube heat exchangers. It's a very efficient way to exchange heat, so to reduce your energy costs. And this can produce somewhere around 30% solids content in your concentrate, so in your disposal liquid or material. And the other one is PCR series, which is scraped. So in this case, rather than forcing the concentrate through a tube heat exchanger, which can have occasionally some scaling or some need for cleaning, basically you have your heat exchanger, which is wrapped around the boiling chamber. And in that way, we can scrape the concentrate. It's a little bit less efficient on energy, but we're able to get 45 to 50% solids in the concentrate. So you have a higher material. The next model is the AC. So this is hot cold water evaporators, and this works fairly similarly in terms of the model options to the heat pump. You have your AC F series, which is your forced circulation, your AC R, which is scraped. Same concepts with the 30% solids versus the 45 to 50% solids. The biggest difference with this model is that we're now able to go up to 15 GPM, so it's a bit bigger. We're still using the strong vacuum to evaporate water at around 100 degrees Fahrenheit or 40 degrees Celsius. The other big difference is it's no longer a completely enclosed unit with the freon gas. We're now going to use heat source from the industry. So if there's a cogeneration on site, you may have a waste heat source. This evaporator is going to take that waste heat source. We're going to run it through the heat exchangers, and that's how we're going to bring in the external heat for evaporation. So you can see that since we're using the vacuum and we're able to evaporate water at these low temperatures, taking that waste heat, which is currently essentially lost in the facility, is now going to be reused as a beneficial use inside of this evaporator. So that's one way that we can really keep our energy consumptions down. The last one that we'll talk is mechanical vapor recompression. So we'll go over a little bit more of a detailed explanation of this in a few slides. But the point here is that it's a bit less of a vacuum. So we're evaporating water at 190 degrees Fahrenheit. But it does handle much larger flows. So we're up to 25 GPM with this. I guess the interesting point here is you saw how compact each unit looked on picture. So this is the largest evaporator we offer, up to 25 GPMs, and you can still see that it's completely self-contained inside of this box. And to give you an idea of the size, the largest Evalid evaporator is still slightly smaller than a standard shipping container. So they're easy to fit on site, and you'll have a compact system for your wastewater treatment. But as I mentioned, we'll get a little bit more into details on this one in about 2 slides. So how do we optimize our heat transfer? This is a neat graphic. It just kind of shows you the lines. We'll spend a little bit of time, but basically the components themselves are relatively self-explanatory. You have a boiling chamber, which is exactly what it sounds like. It's where the liquid is going from, well, it's going from the liquid to the vapor phase. You have an external heat exchanger where we're providing the energy for the evaporation heat. So we can do clean in place as available to reduce labor costs if needed. We have a condense heat exchanger. So when we convert that vapor to a liquid, even though it's transformed back into a liquid, there's still a lot of heat in that liquid that we can use to recover. So that's going to go through a heat exchanger. There's a circulation pump, which pushes at a high velocity through the tubes of the heat exchanger. And then there's the venturi ejector pump, which creates our vacuum conditions. So it's just closed loop. Everything's running around in series. And if we take a closer look at the mechanical vapor recompression, this again is a schematic, which I'll go over in a little bit more detail. So basically we'll start with the boiling chamber. So basically this is where your liquid is. You'll have your vapor at the top. You'll have your concentrate here at the bottom. Your vapor is then sucked through this blower. So basically it's compressed, it's sucked through this line. This vapor is basically then turned into a hot steam. This goes through a heat exchanger. As it's going through the heat exchanger, it condenses, so it transforms into a liquid, goes into this condensate holding. So this condensate here is still at around 80 degrees Celsius. So there's a lot of heat here, and you really don't want to necessarily discharge 80 degrees Celsius water. So we then run this condensate through another heat exchanger where it goes from about 80 degrees Celsius down to 40 degrees Celsius with its interaction in the raw wastewater. Your concentrate line, basically what's inside of your concentrate here goes through, and it's going through this heat exchanger with the vapor. But the important point here is that you're always going to be discharging a portion of this condensate. It starts on semi-continuous, but once the system running, it can be a continuous discharge of the concentrate, so it's easy to operate. The discharge is more or less controlled on time or density. So basically, once you reach certain densities, then the concentrate will be ejected. So they're really a self-contained system, and as I mentioned, it's all standard units with the remote support. So we have a lot of support to the operators as well. So now I'll turn it over to Michele, who will give you an update on some case studies throughout the world.
Hello, everyone. Thank you Bradley, for the introduction, and thank you everyone to hear our technologies. Okay, so first of all, I want to introduce our case studies. We have over than 50 installations currently running in the US. Both and also we have installation all over the Americas, from Canada to Argentina. Okay, first of all, I want to talk about one of our bread and butter application, the automotive sector. In this case, I want to show you a US company that makes automotive components, in particular brake and control system. And they had water coming from the washing line for the metallic part. This water was really very high polluted, and they have to track off this water because no one, and for sure the flow rate was limited, and no other technologies, no other water technologies can treat water like this due for the high conductivity, high phosphorus rate, high surfactants. So with Evalet, we are able to treat this water and get a reduction of 75% of this waste. So as you can see, we reduce their waste and their disposal cost up to 75%, and it means 4 times. And on the other hand, they were able to reuse the distillate in their production because the quality of the distillate reach their limits in order to recreate the cleaning liquid and the cleaning solution for the cleaning parts. Another case study, this is another very important case study, very unique case studies. We had different corporate, different location that use Evalet in this company, in this corporate. They produce candy, and they have wastewater coming from the cleaning of the all the reactors, all the equipment that have in direct contact with the manufacturing of the candies. And they pay a lot this wastewater in order to track off. So with Evalet, just with a small pH correction in order to keep all the COD and all the main component, main critical components into the distillate, we add a pH correction. In this particular case, we had a total solid of around 3–4%, and mainly was sugar. And as you can see on the COD and the BOD. With all the other water technologies, is a little bit tough to treat the water with a lot of sugar. So the only way to treat this water is to evaporate the water and collect the sugar. In this particular case, the customer was able to concentrate the stream 10 times, and reuse and sell the concentrates as animal feed to the farmer to feed the pork. As you can see, they also was complied with the regulation of the water, and they are able to sell to discharge the distillate direct to the sewage. Another very important case study for food and beverage is to treat whey milk. Whey milk is another great issue for the conventional wastewater treatment. So in this particular small cheese factory, we treat the whey milk, and with the installation of the Evalet, we are able to first of all recover the valuable part of the whey milk, and they are able to sell the whey milk and to reduce for sure the disposal cost that they had before the installation of the Evalet. As you can see, at the beginning, the dry matter, the total solids, was very high, and a very high conductivity, very high COD, a lot of chlorides because of the salts that they use for making the cheese. So they treat around 20 cubic meter per day of water. They separate. So with the Evalet, we separate the water from the whey milk. The whey milk was recovered and sold as bioproduct for animal feed, like in Ferrero. And the distillate, they were able to sell, to reuse the distillate in their facility to clean the floor or to other low valuable use. As you can see, the water that we produce is clear water, and due to the fact that we have both the advantages. First of all, water reuse, and second one, the sale of the bioproduct. The return of investment in this case was very small, less than 1 year. We're talking about 10 months of return of investment. And due to the fact that for this application we use a heat pump, we are able to reduce the production of the Escherichia coli into both into the water and into the whey milk. So we and for this, in this case, we save money for the customer. Okay, I'm just switching on all some of the most important case studies that we had. In this case, we are facing with the problem with the pharma, and in particular with active ingredients inside the wastewater coming from equipment washing for the pharma production. In this case, we are talking about around 8-9 tons per day of wastewater, and the main problem for the customer was the API that they have in their wastewater. Normally, they track off the water, but in this, with the Evalet, they were able to separate the water from the API with a reduction of 99% of the API, or higher than 99%. It means that the water was clear, and they were able to send directly to the sewer. And on the other hand, they had around the 5% of the 7% of the water to dispose, but we save 93% of their initial cost. As you can see, the machine that is completely on the skid is very compact and fit completely in a room. And you can see as well the desk on the side, and you can see the how small is the unit compared with other and the most sophisticated and complex chain of wastewater treatment. Last but not least, with Evaporation, we also treat water coming from other unit operation. As Bradley said before, Evaporation can be installed as standalone or in a complete chain. In this case, we are talking about a complete chain because we treat the RO coming from a complete wastewater treatment plant that generates zero liquid discharge of the chromium-6 produced by this mining in Utah. So, as you can see, the Evaporation is a part of the ZLD, zero liquid discharge plant. We are talking about multi-flow softening, filtration, reverse osmosis, and the concentrate of the reverse osmosis is treated with one of the biggest application, biggest installation in the world for Evaporation. Two of the biggest unit plus 2 ACR. So we have the two-step evaporation. In the first step, we use the forced circulation in order to get around 25–30% of solid into the concentrate, then further concentrate the concentrate of the RVF with the ACR, where we are able to reach 75% of solid into the concentrate. The concentrate of the ACR is discharged as solid waste, so they can send to the landfill, and the distillate they reuse in their process in order to save the water and reach the zero liquid discharge. In this case, due to the fact that we reach the zero liquid discharge, we reach the 98% of water reuse, and we reach a very high concentration factor, 40 times. As you can see, the quality of the distillate in all the case study is very and pretty high, due to the fact that we separate all the pollutants from the water from the pollutants. How we operate during the a phase of the project.
Okay, I think at this time we're going to hand this webinar back to Bradley Young. Bradley?
Yeah, so basically when a project comes in, it's no secret that Veolia is a large company, and our Evaporation technology was invented in Italy. It's the technical hub. So basically inside of VWT Italy, where Michele is, they have access to more than 1,000 different places where they've tested water with evaporation. So they're a very strong global presence. But what's important in North America is to understand that with Veolia, you're always going to be working with people in North America. So we have process expertise located in Canada, process expertise located in the United States, and you're going to be working with our local expertise, and then we will collaborate with VWT Italy. And by doing so, we're going to be able to do the best estimates of the risk involved in the treatment and make sure that we choose the right equipment for you. So this really comes down to technology, the size, the materials, if there's technology required for pre and post treatments. So we kind of call it a global approach, where you'll always have access to your local people, but you're going to get the global view on the market. The activities that are done, basically sampling, laboratory pilot, chemical analysis, data evaluation, and we have pilots. Another interesting thing to know is that if there is a more difficult wastewater source, or if you're interested in knowing how would my wastewater source handle in a valid evaporation system, we do have access to a large database, but we also have an extensive lab capability. So in the United States, in New Jersey, we have a full lab facility where if you send us a sample of your water, we're able in-house to do testing. We'll provide the report. We'll be able to come out with some estimations and really give you a good idea of if evaluate and evaporation is the right fit for your facility. So just to reiterate again, this helps us leverage everything that we have to offer and provide the most local and the best support for for each of the individual clients. So to conclude what we presented on the webinar, the key takeaways is that the entire game we're trying to play is the least energy for evaporation as possible to really keep your operational costs down. When possible, we want to use your distillate. We want to use that water that we've created as a beneficial reuse. You saw a few of those case studies where that was certainly feasible. Achieve corporate sustainability goals, zero liquid discharge. If there's any byproducts that we're able to recover, then we really want to harness these. Small footprint. You could probably see by McKelly's case studies also that a lot of those units were located in small spaces. I think most obvious was where you saw the desk sitting right beside the evalet, and then it was quite tiny. And to know that there's various type of evaporation technology. So if you have cogen facility on site, we may be able to look at using some of your waste heat. If you have a smaller flow, we can go more with those heat pump. And if you have a bit of a larger facility, then we can go with more of those mechanical vapor recompression. All standard products, standard models, so we can really find something that's fitting inside of those windows. So with that, I'll hand it back over to TJ, and we'll invite you guys to ask your questions.
Thank you so much, Bradley, and thank you for McKelly for sharing the technical background for this evaporation technology and also going through a lot of case studies. Just one thing to add, we, due to time constraints, we could only share a small number of case studies. So if you are attending this webinar and you're from an industry that wasn't represented in today's presentation on the case studies, please get in touch with me or any of the panelists. We want to share any case studies we have. We have quite a few that might just make it a little bit more tangible to understand what this technology might mean for your industry. So we're going to transition now to our question and answer session of today's webinar broadcast. We have quite a few questions here, so we're going to try to get to as many as possible in the time that we have left. I'm going to start off with one. Bradley, can you tell a little bit about the range of flows for this technology?
Yeah, so basically the heat pump model, we can go small flows, so up to 5 GPM. Once you get more than 5 GPM, then that's the upper limit of that product range. With the hot-cold evaporator, we have 5, 10, and 15 GPM models. So if you fit in one of those ranges. And then with the mechanical vapor recompression, we can go up to 25 GPM.
And just can you just even elaborate a little bit more on the differences between the three different categories of units as well?
In which way? Sorry.
Just can you tell a little bit about the differences between the three categories of Evalad units?
Oh, sure. So basic, like how they operate?
Yeah, the main differences between the three versions.
Yeah, so the main difference between the heat pump and the hot cold is that the heat pump is self-contained. So I think I mentioned it's similar to like an air conditioner where you have a freon gas loop. So you don't need an external hot water source coming in, but it is at that smaller range. When we're looking at the hot cold, we need a hot water source to be present. So if you have a cogeneration facility, then we'll use some of that heat you have available on site. And then for the mechanical vapor recompression, we're going to have an external heat source there that we provide as well. So we don't need hot cold, but that will get you some of these larger flows. So really when you have your project, when you come to us, if you can give us an overview of what's available on site, the flow rates you have, and then we'll tailor-made which model will best fit. But really it's going to come down to flow rates. There's some overlap there. But then aside from flow rates, we're also going to look at what we can use from what you have on your facility to reduce those energy costs.
Okay. McKelly, I have a question here asking about what other cogen hot and cold sources have we paired the Evalad up with? Can you comment on?
Yeah, we can pair the ACF with the hot water, with the hot oil or the thermic oil, or with steam. So all three of these hot source can be coupled with the Evalad, with the ACF technology. or the ACR as well.
And are these just coming off the customer's traditional utilities?
Yeah.
Okay.
Correct. So you can use the steam or steam from boiling, or hot water, or hot oil, the thermic oil. So different source, that all the heat source that you have available. We can check if the flow rates and the characteristic can be coupled with the avalanche, and they can easily fit the avalanche with their utilities.
And that's a good point. We have another question, Kelly. When you're doing feasibility studies, it's easy to, you shared about how we have the lab in Philadelphia that analyzes and can perform that on the waste stream. But what do you do to check the feasibility on these external temperature sources?
No, what we do, we know how much heat we need in order to heat up the water, and how much water we can evaporate if you have this heat available on site. So if you have a flow rate of an amount of water, we can tell you how much water you can evaporate and how much heat you have to provide in order to evaporate that water. And if your heat is enough, if you have enough utilities to do that, we suggest you would go with the ACF. On the other hand, if it is not enough and your heat source is too small, we go with the RVF, because the ACF and the RVF are complementary. So you have the same size for the ECF and the RVF. It depends about how much heat you have. But on the feasibility study, we test how efficient is the evaporation, if the forced circulation, and how much distillate yield we can reach on, both the technology works at the same. So ACF or RVF works the same. The important thing is that how much distillation we can reach, how much water we can recover. This is the test that we perform during the evaporation.
Okay. I have a handful of questions related to economics and when is this technology cost effective? I know that's a loaded question, and it normally depends. But
Yeah.
can you make some comments about economics and cost effectiveness of this technology?
Sure. We are talking about a rough cost of $10–12 per cubic meter of water distillate. Okay, so if this is the average OPEX cost. For sure, the main drive is how much they pay, how much the customer pays for the disposal of the water. So if they pay around $50 to $60 per tons, it's okay to invest with Everett. If they pay less than this value, maybe the dispose, or maybe the truck off the water is still convenient.
Okay.
I can add to that a bit too. When a project comes in, we can also assist if we are given the information for how much you're being charged for disposal. And then we can select the valid model, and then we can do a comparison, and we can run it out on an NPV of however many years. We can calculate a payback. So we'll support in that inquiry if we are just provided with the information of what's on site and how much you're paying for your disposal.
And just to add to what Bradley was saying too, and what Kelly, but also we have several other technologies that we could use upstream as a pre-treatment before going into Evalad to make sure it's optimized in terms of whatever that influence needs to be. A question back to temperature. How do you decide? sort of the temperature that needs to be maintained on the application? Does it vary on the influent that's coming in? Can you comment a little bit about that?
No, the temperature is fixed. So the PCF and the ACF work at lower temperature, the lowest temperature possible, and the lowest vacuum, around, let me say, 85, 90 Fahrenheit degrees. So we keep the temperature stable in order to evaporate at the lowest temperature and at the maximum flow rate the water. On the other hand, the mechanical vapor compression doesn't reach so deep vacuum, so we work at higher temperature at 170, 190 Fahrenheit degrees. But
Okay.
this is the temperature. Lower temperature, ACF, PCF, higher temperature, RVF.
There's a series of questions here related to total dissolved solids. Can you comment on the ranges of TDS that could be influent, and then what to expect in the quality of the distillate and the concentrate?
The distillate could be completely free of TDS. We are talking about an influent of, for example, 10,000 ppm of TDS. We could have 50 to 100 ppm of TDS into the distillate. On the other hand, all the TDS will go into the concentrate. What about the limit? Okay, as Bradley said, we have limit on the concentrate, on the TDS that we can reach on the concentrate. For the forced circulation, we can reach 30%. It means 300,000 ppm. With the scraped, we can reach up to 85%. It means 850,000 ppm of TDS. What about the influent? It depends. It depends of the influent, because much more concentrated is the influent, less is the concentration factor that we can get into the evaporator. So we can treat water with all the range from 0 TDS up to, let me say, 150,000 ppm of TDS. This is more or less the range that we can treat.
Also, can you talk about maybe some unique streams, maybe low pH streams, and how this technology could work for acidic wastewater streams?
Okay, about low pH, it depends about how much low is the pH and what is the reason, or the reason of why is so low the pH. Because it depends. The pH can be low for acid, or for chromium, or for chromium 6, or for other reason. But we can easily treat different corrosion level, because we provide the unit in different materials. We can provide the unit with stainless steel if the chlorides are not too high. If the water is rich in chlorides, we can go with the super duplex that can reach much more higher concentration of chlorides and much more lower pH, because we can have some corrosion if we use the stainless steel. If the super duplex is still not enough, we can go with the Hastelloy. Okay, so we have a variety of materials where we can provide the machine, we can manufacture the machine in different materials. So it depends about what is the reason of this low pH, and what is the level of chlorides or fluorides or acid level inside the wastewater. But we can treat different streams, different pH level, let me say.
Okay. have a handful of questions on sort of what to do with the water reuse, and also how to, whatever the people, current customers are using to recover the byproduct. Can you talk about maybe some unique applications where people are using water after going through the EvaLad, or can you talk about what people are doing with some of the byproducts that are being recovered?
Okay. Some of our customers, for example, in food and beverage, like in the candy candy manufacturer, they use the concentrate as animal feed. Other, for example, in some of our case, we have in the automotive sector or into the mechanical surface treatment, we treat water coming from plating line or from chromium plating line, where they have valuable components into their waste. They concentrate the waste and they use the concentrate in order to feed the, for example, chromium bath or the nickel bath, because the concentrate is still a valuable matter. It's not like pure zinc or pure chromium, but it's still valuable, and they can reuse this concentrate. Other kind of reuse resell the product. We have an application into the pot tail production, where the customer is able to concentrate the pot tail coming from the whiskey distillery, and they reach 45% of solids with the pot tail, and they sell this component as bioproduct for other production, and for a fertilizer in particular. Other reuse. In the automotive sector, we treat a lot of wastewater with oil emulsion, or other kind of oil. And some customers are able to concentrate this oil and burn this oil in order to create heat. What about the use of the distillate? Some of our customers use it for cleaning or for irrigation, for low valuable use, not for process use, because even if the water is clear and we can easily discharge the unit, the distillate is not processed water, it's not dry water. But in some automotive application, they can clean they can use the water to clean the piece again, because it's still good. They can reuse to clean the floor, or to feed a row, or to their row, in order to create, or the process a row in order to create clear water again, and dilute the water, the RO water. So we can reuse the water in different way.
Okay, well, we have still a lot of questions that I try to group as many as possible. But what we're going to do is we're going to get back to our technical team here and go through these questions and see if any that weren't answered, if we could get back in touch with those. So we have your record of question, and we'll try to get back to it. If there's something that's real pressing that you need to ask, feel free to reach out to me, myself, TJ Willits, and I'll direct it to the right contact. But we'll be in follow-up if you need anything else. So if you could just advance that to the next slide, Brad. Again, the survey will be given to you right after the webinar. Take a few moments to fill that out, and again, we'll enter that yourself into a $25 Amazon gift card. This webinar is being recorded, and you'll receive a recording link within 24 hours of this webinar, so you can rewatch this webinar on demand. So at this time, we're going to conclude the webinar. I want to thank both of our panelists for spending time with us and sharing their technical knowledge with everyone here. And also, I'd like to thank anyone who attended today's webinar. It meant a lot for you to share a little bit of time out of your day and learn a little bit more about these evaporation technologies. Again, my name is TJ Willits with Veolia Water Technologies. I want to wish everyone a great day and a great week. Take care.